The basic parallel algorithm that we have developed can be improved by a technique called two-phase broadcasting. A definition that we will use sometimes is the definition of communication volume. The communication volume of an H relation is the total amount of data words that's being communicated, and you can obtain that by taking for every processor S the amount of data being sent by S and add this up. Of course, you can also do that by adding up how much every processor receives, and we assume that no messages get lost in the transferal. The total communication volume V of an H relation is at most P times H, because every processor sends and receives at most H data. If we have equality, V equals P times H, then we can prove that every processor must send H exactly and also receive H data words exactly. So if that happens, then we call the H relation balanced. And in an H relation that is balanced, we do have that the maximum amount sent by a processor, H sent, equals the maximum amount received. Question to you: is the reverse of this statement true? So if we have H send equals H received, then does it hold that the H relation is balanced? The answer is no. If we have an H relation that is balanced, we do get H sent equals H received. But on the other hand, if we have this equality, it could be that one processor is very busy sending, another is very busy receiving, and the others don't have to do a lot. And then we don't have a balanced H relation. Now let's look at what happens inside LU decomposition. H send is 2 times RK plus 1 times square root P minus 1 in case we have a square cyclic distribution. But what processors receive is just 2 times RK plus 1. We do have an imbalance here. H send is much larger than H received, and this means that we must improve the algorithm by reducing the communication cost. Because if there's a lot more sending than receiving going on, meaning that some processors are overloaded, we must reduce that. And then hopefully we can achieve the value of H received. A technique to do that is two-phase broadcasting, and what we have done so far was one-phase broadcasting. Here's the problem, not for LU decomposition, but for a simple situation where we have a vector x of length n that is available in processor 0, and we want it to be available in all processors. So the straightforward way to do this is to write the algorithm for processor PS, because we are always processor PS in the one-dimensional numbering. And the algorithm then is, if S equals 0, if I have the data, I have to send it to all other processors, the target processors, 1 up to P minus 1. And I have to send all the data xi with I between 0 and n minus 1. I put xi in PT, the target processor. Very simple. If we do it in two phases, processor 0 just takes care to get rid of all the data, sending them not to all processors, but every data element to one processor. Here we have the situation where we have a block size B of 3, and processor 0 sends out, it has 12 elements, but it sends to each of the other processors a quarter of the data, and it also keeps the first part to itself. That's the first super step. And then when the data are spread across the system, then every processor starts sending to all the others except processor 0, because we're not sending back data to where it already came from. So processor 0 will in this case send its block to processors 1, 2, and 3. Processor 1 will send to 2 and 3. Processor 2 will send to 1 and 3, and so on. How do we formulate a two-phase broadcast? Here we do that again for processor PS. We assume a block size of n divided by p. We assume we do not need to round in this example. So the first super step is spreading the data. If s equals 0, then I send to all the processors, not all the data, but a block of data. So if we're sending something to processor T, then the block will be from TB to T plus 1 times B. And that's what we put in that processor. That's the block the processor PT becomes responsible for. Then everybody has a block, and then everybody sends its own block. So what do? You send to all the processors 1 to p minus 1. You send the block that you are responsible for. And since I'm processor S and this program text is for me, my block starts at SB. It ends at S plus 1B minus 1. And that block I'm going to put in all the other processors, except not to 0, because we know already that that processor has the data. So what is the cost of this algorithm? Phase 0 is just getting all the data out of the door, n minus b data. I keep my local block, I don't send it. So the cost is n minus b times g. And then phase 1, every processor has a block of length b and sends it to at most p minus 1 others. For example, processor 0 will send to exactly p minus 1 others. So the cost is p minus 1 times b times g. We can add them up, and then we get n plus p minus 2 times b times g, because g is the time per data word. And we do have 2 super steps, so we have 2 synchronizations, 2L. And then we can compare the cost that we get, which is about 2 times n times g plus 2L, with the cost of a one-phase broadcast, which is p minus 1 times n times g plus L. So you see, we have reduced the communication costs by about a factor p divided by 2, at the expense of an increase in synchronization cost by a factor of 2. In LU decomposition, then we can use this technique to send all the data. For example, if we want to send the red data, which are the elements of column K of the matrix, so all the AIK that are mine, I'm going to send from their position, which is processor S, K mod n, because it's column K by the cyclic distribution, and I want it in the whole processor row S. That's the statement. And we do this for every processor row at the same time. And we can combine the phase 0 of the row and the column broadcasts, just saving a synchronization, and then combine the phases 1 as well. So what do we get then? Then we have a cost which reduces to the cost that was for the receiving, and that cost is 2 times rk plus 1 plus ck plus 1 times g. We can bound this cost, and by a similar technique as we've seen before, we see that we have an upper bound which involves m plus n divided by p, and this is minimal again for a square distribution, which is nice because then also for this improved algorithm we still have that the square distribution is optimal. The total time that we get consists of 2n cubed divided by 3p, that's the main term for computation, and that's the sequential time divided by p, which is good. This is what we hoped for. Then we have a second term, which is load imbalance, but it looks almost like the third term, except that the third term has a factor g, because that's for communication cost. So the load imbalance will be less important than the communication time that we have. And when would our algorithm be efficient? That is, if computation time dominates communication time. So we can compare the two terms that correspond to these computation and computation time. And then we see that we need an n, a problem size, to be at least 4.5 times the square root of p times g. So for n large enough, that we have an efficient algorithm comparing computation through communication. So the efficiency is also determined by comparing the computation cost with the synchronization cost. And the synchronization cost is 8 times NL. And that also gives us an n which should be at least 2 times the square root of 3pl. And because of that square root, the synchronization cost of a single synchronization is less important. You can also say because we have an n in this cost formula instead of n cubed for the computation, synchronization cost is less important. So what did we do? We analyzed the algorithm, made a cost analysis, and we diagnosed a problem. H sent is much larger than H received, meaning that there is hope to reduce the communication cost to H received. And this motivated us to develop two-phase broadcasting. And the two-phase broadcasting idea is to spread the data first and then start communicating them to all processors. A question to you, final question. Assume that we have a BSP computer with P equals 10 processors, G equals 100, L equals 10,000, and we want to communicate a vector n, a vector x of length n, to all processors. We want to broadcast a vector. We have the choice between one-phase broadcast with the cost T1 and two-phase broadcast with the cost T2. When would you choose the two-phase broadcast? For which n?